Right, so welcome to week 8. I think, again, I'm ahead of Taiwan at the moment. I think Taiwan's... Do you know what he's still doing at the moment? Have you reached shear yet, or is it still beam design? Okay, fair enough. He might be starting shear right now, which is what we did last week, right? Yes, shear.
That was the shear force diagrams we did.
Oh yeah. That's the first step for shear. So he probably. Okay. Well then. Okay. But anyway, we're up to serviceability.
Oh yeah.
And then Taiwan will probably start serviceability next week, and then for me in week 9 I'm going to do slabs, which needs to use. You need to know flexure, shear, and serviceability for slabs, but it's not that much harder. It's just like combining them all for something other than a beam. And then for week 10, it's going to be columns, which is like kind of completely different. that week 10 one's going to take the longest, I think, to run through everything. But for week 9, it should be pretty chill. Serviceability, I don't know if... sorry, Johnny, just to pick your brain for a second. Do you reckon serviceability is hard for concrete compared to like strength and stuff? It's just different. I don't know if the whole process of serviceability is quite different to strength. So you guys haven't done serviceability yet, even if you've done steels, because like for steel design, at least at UNSW, we don't really touch serviceability. So it's kind of a new concept. It's basically about like 2 things. One is limiting the max amount of deflection that we have, and then for your structural member, and then the other thing is crack control, stuff like that, right? So typically when we think of deflections, we think about slabs because they deflect more. It's one of like the limiting factors rather than beams. So like, for example, this roof of this room, that's a slab. It's basically like a 2D version of a beam, right? And you can imagine like the max amount of sagging might occur like in the middle. So if you just looked up in the ceiling right now and then it's fucking sagging down, you'd be like, okay, well, something's wrong with this fucking room, right? So yeah, anyway, so that's what we had designed for essentially, right? So basically in AS3600, so this is now becoming specific to concrete. There's 3 levels. There's your low-level design, mid-level design, and high-level design. So lowest level design, it's actually covered in advanced concrete, but like it's like half a week's content. It's basically like a really quick check to see whether your beam or slab passes like the serviceability test. It doesn't really help you with what is the best dimensions or whatever to design your beam so that it passes this test. It just checks whether you've done it or not, right? So it's called deemed to comply, right? The level that we concentrate on in this course is called the mid-level, which is like you have a deflection amount that you calculate and you compare it to some allowable limit, which depends on the span of your beam, right? And then high level ones, if you want to like save more materials while still passing the serviceability check, you need to use like software analysis. So you can't do it by hand basically, right? Yeah. Any questions so far? Yeah. So so these are basically the 2 structural equations we've seen so far in this course. We've seen the flexure one, and we've seen the shear one now, right? If you've done steels, you've seen the axial ones for. Okay, I think it just Jordan's on. But you've seen like the axial ones for tension and compression, but they're just like a variation on this basic structural. Wait, did you do steels?
Yeah, I did.
Okay, anyway, yeah.
Just like you forgot.
It's just like a variation on this basic structural formula. So we're going to do a similar one, except it's for serviceability, right? So the maximum deflection has to be less than some limit, right? I was trying to think of whether it was better to arrange the information like this or like this, but I think in my head it makes more sense to say like this. But if you want to think about it in terms of like internal actions and external actions, then For loads, generally that's your external action, and then capacity is the internal response from your member, right? Your structural member. Whereas max deflection is actually the equivalent of capacity. You know what I mean? Your max deflection is your internal response, while the deflection is like an external kind of factor. So I've kind of swapped the sides, if that makes sense. I'm going to start by talking about the limit, right? So that limit on deflection is from this table down here. So the only one we really focus on in this course is that top row, right? So this is from AS 3600, and it says that the deflection limit for simply supported beams and continuous beams is 1/250, and so this ratio is multiplied by your deflection over the effective length, right? So basically, why it has to do that is because these deflection limits have to be relative to the span of your beam. So if you can imagine, like, I don't know, this pen is my span, right? It's not going to deflect very much. But if this is like 10 times bigger, it's going to deflect by a lot more, right? So you have to scale it based on the size of the member, right? Like the length of the member. And then there's a different one for cantilevers as well. So that limit is 1 on 125, right? So I've just summarized that using this, right? But again, that's to do with your limit, right? Your total deflection, we're going to calculate that on the next page. So we'll do that. But before I do that, I just want to talk about the effective span, right? So the effective span is going to be the worst case scenario between two things, as in the minimum. Worst case scenario. I wouldn't call it the worst case scenario because a shorter span is actually going to be like a shorter span is going to result in less deflection. But anyway, so I think what it's saying is like you want to take the minimum number between the actual length, so that's the center to center length, right? So if we have like a simply supported beam, that's just like your regular length, right? And your clear span plus the section depth, right? So sometimes this number is actually the governing number because it's smaller. Does that make sense, guys? So that's just the definition of effective span. So whenever you see effective span, you have to do that like small calc to get the minimum between these two numbers, right? Okay, so let's talk about max deflection, right? So, at these various support conditions, right? Your simply supported beam, your cantilever, and your continuous beam. There's going to be different points at which they have maximum deflection. Oh, firstly, what is deflection? Like, do you guys understand like the general concept of deflection? It's basically how far it's warped, like your beam has warped from where it's supposed to be, right? Like if it's sitting straight, right? So for a simply supported beam, it deflects the most in the middle, right? Yeah.
Wait, is it the same deflection from 2400?
Yeah. And then for a cantilever, it deflects the most on the free end, right? So think of it like a diving board, right? The free end is going to deflect the most. But the thing is about that cantilever or the diving board case, you can think of it like that, is the maximum moment is actually going to be at the support, but the maximum deflection is going to be at the free end, right? So just keep that in mind, yeah? Okay. The continuous, for a continuous beam, it's actually quite complicated. The deflection looks roughly like this, right? But because of the complexity of it, we actually just only really care about the deflection in the middle of each of these spans, right? So the max deflection might actually be like slightly offset to the side, but we just take it as the middle because it makes our calculations easier. That we don't need to find the exact location of that max deflection, right? Oh, and just some terminology. These are called end spans, and this is called an interior span when you have a continuous beam with multiple pin supports or whatever. Multiple supports, you can just think of it like that.
Wait, so the rule is always taken in the middle, right?
Sorry?
It's always taken in the middle, right?
Yep. Okay, what if we have a continuous beam that looks like this? What's this type of span called?
End span.
What about that one?
End span.
Very good. Yeah. So it's actually simpler than you think it is. There's only an interior span when you have 3 or more spans. Yeah.
Is it always going to be symmetrical? As in like,
Oh, I know what you mean. Typically, yes, because if the spans are different lengths, and a continuous beam is statically indeterminate, right? So like in 1300, you don't really deal with continuous beams because they're actually too hard to solve. You learn about how to solve it properly in like 2303, but it's actually way too AIDS to solve. So in 3600, right? You're going to see later, we have simplifications for what like the bending moments and what the shear forces are at these supports, but only if they're the same span. Is it right? I think so.
same distance.
That we'll get to it when we see that diagram I've included, but I'm pretty sure it only works if they're the same span for all of them. Yeah.
But in real life, usually they would be the same span, right? When they're constructing.
Not necessarily. I mean, it could be for ease of fabrication, but there could be something you need a shorter span for, a long span for. You know?
Okay.
Yeah. Okay, so basically, okay, let's just concentrate on the simply supported beam, right? So that total deflection, right, in the middle, that can be broken up into smaller parts, right? And we break it up based on the time span, right? So what we call it short-term deflection and long-term deflection. In soils, right? You call it. Have you heard of like elastic responsive soil and stuff like that? That's just like instantaneous, for example, deflection, right? So there's like a part that happens almost immediately for the deflection, and then the part that happens over a long time, right? I think it's in soil sediment or something like that, yeah. But anyway, so the total can be thought of as this red part here, right? And then the short-term portion is that elastic portion I was talking about, which is just another way of saying it happens nearly instantly, right? And then we have our sustained deflection and our long-term deflection. So the sustained deflection, how do I do this? Sustained deflection, we don't actually really think of, how do I say this? It's basically an intermediate step. So we only really need to think of what the short-term deflection is and the long-term deflection, and when we add those two portions together, we get the total, right? The sustained deflection is purely a mathematical step in order to get the long-term one. Okay. Yeah, and then the order you calculate everything. You want to start with short-term, sustained, which again is your intermediate mathematical step, to get the long-term deflection, and you literally just add those 1 and 3 together, and you get the total, right? Okay, so before we do anything to do with serviceability, we need to really understand what the objective is of the question, because depending on whether you have a simply supported beam, cantilever beam, continuous beam, especially continuous beams, like it can get pretty complicated as to how many cross sections you need, right? You need to figure out how many cross sections you need to calculate, and you need to figure out where they are, right? That's the difficult part. Once you've sorted that out, the rest of the calculations is just following through, basically, right? But if you get this initial guess wrong, your life's gonna be really tough, okay? All right. It's because this is the mega formula, right? You'll see this later. IEF, average. This is what we're aiming for in order to calculate the deflections, right? It's an average moment of inertia along the span. Okay. So basically, if you have a simply supported beam, you only need the effective moment of inertia in the middle, right? If we have a cantilever, we only need the effective average at the support, right? So let's go back up. For a simply supported, we only need that effective moment of inertia in the middle. For a cantilever, we only need it at the support, right? So if the max deflection is over here, why do we need it at the support for a cantilever? Someone give this a crack.
Wait, what was the question, sir?
The question is, why are we analyzing the effective moment of inertia for a cantilever at the support rather than the free end? Even though the free end is where it's deflecting the most.
The maximum is at the.
Very good.
Yeah.
We care about it because that's where the maximum is. Very good, Father. Okay, for a continuous beam, it depends on whether it's an end span or an interior span, yeah? For an end span, right, we only need 2 points, right? We need it at the middle and we need it at the continuous end, right? So let's go back up. So an end span, we need it in the middle, and which one is the continuous end of the end span?
Continuous end.
Is it going to be to the left or the right left or right of the blue line I just drew?
Right.
Very good. So that's a continuous end. Because this is the non-continuous end. It's like a dead end, right? So on this side, would it be on the left or the right?
The left.
Very good.
Okay. Right.
So for an interior span, right? For an interior span, we need it in the middle and both the ends, right? So let's do that again. For an interior span, we need it in the middle and then left or right?
Both.
Very good. We need it in both. So if we need an interior span, if we need to calculate the deflection of an interior span of a continuous beam, we need to do 3 cross sections of calculations.
Isn't it? Okay.
Oh yeah, I know what you're going to say. You're going to say these are the same, right? Sometimes they are, sometimes it can be different.
Okay.
Yeah.
Right, so other three, so both left and right, and then also in the middle.
Sir?
You said you need 3 cross-sectional measures. Is it also in the middle, the very middle one?
Yeah. So always, for continuous beams, always take the middle.
Yeah.
For a simply supported beam, always take the middle. For a cantilever, always take the support. So the rule is written here. So wherever it says mid, you need to include the mid, right? Okay. So firstly, let's go back for a second. What is effective moment of inertia? Okay. Firstly, what is moment of inertia?
Resistance to bend.
Very good. It's bending resistance based on your cross-sectional area, right? So basically, effective moment of inertia is a concept that's only specific to concrete, right? It's because we've talked about the idea of cracked moment of inertia, right? Like you guys in like week 4 or whatever, you calculated the cracked moment of inertia. So does anyone remember the exact definition of cracked moment of inertia?
The moment at which cracking occurs.
That's cracked moment actually.
Isn't it the moment before, like just before cracking?
So we're thinking about it kind of in the wrong thing, like wrong context. You guys are still thinking about the moment. This is the moment of inertia. This is this
That's right.
this is m to the power of 4, whereas this is in whatever, like kilonewton meters or newton millimeters, right? So let's not think of external forces. This is like more similar to something like area, right? So that bending resistance, which is a geometric property, right? In the cracked stage of concrete, you basically assume all of this bottom concrete is cracked, right? And then you take what that moment of inertia calculation is. So you only consider the top bit of concrete and then the compressive steel, tensile steel. And you use that whole centroid formula for for the transform section. Yeah, do you remember in solid mechanics there's like those beams with like the fucking timber and steel and you use modular ratio method? It's the same shit, but we turn the steel into concrete.
Yep.
And then pretend that all the concrete below this line is cracked. Or zero, effectively, zero area. Sorry?
So we just ignore the concrete below.
Yeah. But it's also a function of, like dn is this part of this concrete rectangle, right?
Yep.
So it's like a quadratic relationship between dn and everything below it being cracked. Do you know what I mean? Yeah. Anyway. But basically, IG, right, is the notation we use for the moment of inertia for the uncracked section. And here's where the neutral axis is just equal to the regular centroid. So the centroid of all this, including like that whole like transformed section, all that stuff, this is the same as the neutral axis. This is where it's going to bend about. Sometimes people ask, is the neutral axis the same thing as the centroid? Why?
Neutral axis is where strain is 0, right?
Yeah?
Yeah.
That's the definition of
The
it.
centroid is just where all the center of mass is.
Yeah, center of area for the
Yeah.
cross section. True. But it is equal before any of the concrete is cracked. Once you have cracking occurring, it's not the same thing anymore. Where it starts bending around, which is the neutral axis, and where that centroid of all that stuff is going to be a different number. This is like a material property of concrete, right? I shouldn't say that. It's not a good word. It's specific to concrete, right? Anyway, so the effective moment of inertia we've finally gotten here is basically saying that some of the concrete might be in this stage, some of the concrete might be in this stage, and so we're kind of like averaging it, I guess. You can think of it like visually like this. So for a simply supported beam, it looks kind of like this, right? Where like most cracking would happen in the middle, right? But we have to take an effective calculation because not all of it has reached that really critical stage yet of the cracked moment of inertia, right? And then for a continuous beam, it looks even more fucked, right? Because we have cracking happening from the tensile side and it's both the tensile side, but there's basically sagging here and hogging here at the support. But not exactly on the support, because on the support, this column provides a bit of rigidity. So there's not as much cracking here, but there's cracking on this side here.
Are those lateral cracks?
Yeah. I haven't drawn any shear cracks on here. Yeah. Okay, makes sense, kind of. And for a cantilever, the cracking happens on the tensile side, but again, the tensile side is on the top. The max moment is here, right? So that's why we have to take that effective moment of inertia calculation from the support side, right? Okay, any questions so far? Okay. Oh, I guess you can think of effective moment of inertia as like an average of the entire beam that we care about, the span of the beam we care about. So, all this here is uncracked, here is cracked, and then effective moment is like, we have like this really complicated calculation for what this effectively is equal to, right? So this moment of inertia. Okay, so do you guys remember this formula, these formulas? So it's partly from solid mechanics, but it's partly from, this is your calculation for when the concrete is completely uncracked. And here's the one for the cracked case, right? Where below the neutral axis, it's all fucked basically, right? But it helps to use this for the compressive concrete in the crack stage, this formula. So you know how we normally do BD cubed on 12 for rectangle?
Yeah.
It's actually better for the cracked concrete to use this one.
Why?
Because, I'll draw it here, right?
Oh wait, I know why now.
Do you want to give it a crack?
No.
Okay.
I don't want to try to explain it, but I think I know why.
So BD cubed, BD cubed on 12 is basically what you want to use for the concrete for the uncracked stage, like over here, right? Because you want to represent the bending resistance due to this rectangle. But over here, right, if you did it for, let's say that's B and that's D, you'd have to shift it, wouldn't you?
Yeah.
Because BD cubed on 12 is just, it would place it like here, that rectangle, right? But then we need to shift it by some parallel axis theorem. So you'd have to shift it up here anyway. But if you do BD cubed on 3, that formula applies for a rectangle spinning about one of its edges.
Edging.
So you know what I mean? So this is already one of the edges, and so you don't need to shift it. Yep.
Also one of them.
Does that make sense? Yeah.
It doesn't matter which edge it is.
Sorry. Okay. When I say that, I mean it can be that edge or that edge. But if you want BD cubed on 3 this way is if your dotted line was like that, and then you spin the rectangle the other way. You know what I mean? Yeah. Okay. So that's the first step. You calculate IG, you calculate IC, I cracked, right? Okay, these are new, but they're actually fairly simple concepts, right? So this is called the tensile reinforcement ratio, and this is called the compressive reinforcement ratio, right? So let's break this down, right? So this is P, firstly, and then instead of for the tensile one, we don't use a T to denote that it's tensile. Trust me, like this is fucking cooked. The notation's cooked. It's from AS3600, right? So this is the steel, right? Tensile steel. What's this? Yep, very good. Okay, so what's this?
Distance of the whole hole.
Not quite, that's D. So this is lowercase d.
Until the reinforcement, like this steel.
So you're on the right track. No, you are on the right track, but specifically from where to where?
Top to middle of the steel.
Outermost electron.
Outermost compressive fiber down to the middle of the tensile layers. That's effective depth, right?
Steel's terminal. Outermost electron. This ICR of the rebar. That's weird.
Okay. Makes sense though, right? What this is? Okay. And then this is the same thing, but we take the compressive steel area, right? Okay. Next, we have to calculate the shrinkage-induced stress for uncracked section. Okay. So basically, firstly, I'll tell you where this plugs in before I explain this formula. Do you remember the calculation for cracking moment, which we did in week 4? Do you know where it's from, firstly? Okay. Basically, cracking moment, like Farhan said, is the moment at which it cracks.
Fuck.
Makes sense, right? But it looks like this. So here's your concrete. That's the reinforcement or whatever. And then here's the stress distribution, right? So it's like that, right? Simply supported. That's your stress on the outermost tensile electron, right? Once that reaches more than FCT.F, right? What's FCT.F? Yes. Oh, flexural tensile strength. Yeah, but you can approximate it using this one, right? If you remember. So once this outermost tensile fiber reaches this, that's what we consider cracked. So that is what determines the cracking moment. Okay. And then you multiply it by Z, and then IG on. Okay, but the thing is, I'm not sure if you've seen this in solid mechanics before, right? Z is equal to I over Y hat. Have you seen that before? Yeah. So Z, right? Sometimes Z can be uneven for the how do I say it? Okay. Basically, it's the centroid of this rectangle in the middle. Why?
Because it's heavy.
Very good. So because there's more steel in the bottom, the centroid's going to be a bit lower, right? It's going to drag the centroid down a bit, right? So is DN going to be half the total depth? No. So DN's going to be a little bit bigger than this one, right? This is big D minus DN, right? But why? Oh, I drew this one wrong. Why is this? Oh, basically, I might write this out first. So this. or Z is the elastic modulus. So it's in millimeters cubed. It's basically an area property, and it only applies in the elastic region of a material like concrete, right? So I stays the same, right? But sometimes if you have a section which has like a different centroid from the top half to the bottom half, right? You can actually have ZB, which is Z for the bottom, and Z top, right? But instead of calling them Z bottom, Z top in concrete, we call them the Z from the tensile side and Z from the compressive side, right? So here we actually care about the Z from the bottom side because it's the tensile side, right? Because cracking happens from the tensile side, right? So when we do IG over D minus Dn, it's because we care about that distance to the neutral axis from the tensile side. Do you know what I mean? So that's where that number comes from. But here's where I've gotten to my point. Sigma CS, right? So this is the stress-induced tensile stress for the uncracked section. What this means is that the cracking moment can crack a little bit sooner than what you'd predict. That's what this subtracts. So it will have a little bit of a lower cracking moment because of this value, which has been subtracted. This is because of, do you remember? Okay, this is back to fucking cement in week 2. Shrinkage due to the cement hardening will cause concrete to like kind of pull together. Like that's the tensile stress induced, right? So that will cause it to crack a little sooner than you'd expect. So this is the value that we're calculating for sigma CS, right? So anyway, let's get back to this. It's basically, this is why we have a really complicated formula for it. But it's a function of a bunch of different stuff, including the reinforcement ratio on the tensile side, compressive side, this elastic modulus of the steel, and then this is called the final design shrinkage strain. Final design shrinkage strain. So again, it's to do with the strain induced from the shrinkage of the concrete due to fucking the cement drying, right? Okay. Where are my notes? Basically, this means short term. So if we want to be accurate for our short-term deflection, we want to use this value, right? And then in a question, it might give it to you like this. But it's approximately equal to the total strain, right? So that's what we say. We just say it's approximately equal and then leave it like that. Another thing to note is that sometimes you get this value. Someone want to say it? Okay, good.
800.
That just means 10 to the minus 6.
Oh,
so you
micro.
Micro, yeah.
Yeah, like a
So you did 800 times micro, right? Yeah. Okay, any questions about that? We haven't even gotten halfway through my notes. I've got 15 minutes. Are you ready? Okay. So, basically, what we'll recap. We've calculated IG, which is the uncracked moment of inertia. We've calculated ICR, the cracked moment of inertia. And then we've calculated M cracking. That's the threshold before it starts cracking, right? Now we have to determine the design loads, the short-term moment, and short-term moment at each section, right? Okay, so here's where it gets a bit cooked. Are we going to use our combinations 1.35G and 1.2G plus 1.5Q?
The serviceability ones.
Are different, right? Very good. So basically, instead of exaggerating our loads, you know, we don't multiply it by 1.2 or 1.5 or 1.35. That's what we do for strength. That's like we exaggerate our loads because it's the worst case scenario, right? For serviceability, we actually reduce our loads a little bit. Okay, so what we do is for the short-term load, we have the dead load as normal, and then we have this reduction factor for the live load called psi S, and then a long-term one is psi L, right? And we can get it from a table. Yeah.
Why are the reduction factors in design
I don't know, but I just know that we use reduction factors because for serviceability, it's just, you know, It's just not as high as like strength. I don't know. They just calculated these were the best numbers for it.
Is that because like cracking happens over a long period of time? So it's, like,
It's not really to do with cracking at this stage. I think these numbers are more to do with the deflection.
Oh.
Like the deflection's better modeled when you under exaggerate the live load. Apparently, is what it says in the code.
Wow.
Yeah.
Is it meant to be like a wait? Isn't the long term factor like smaller than the
Yep.
short?
Yep.
Yeah.
Okay. So the typical numbers is for short term 0.7, and then for long term 0.4. But it can change. But I've just included all the cases here. Okay. So short term design moment. We have to calculate the bending moment essentially, but instead of with your exaggerated W star, we use this W star S, which is our under exaggerated load combination, right? We use the flexural span, just like before, for a simply supported beam. Everyone remember what the flexural span is? Yeah, but it's like this. So this part here is the flexural span, right?
Yeah, that's right.
Yeah. So it's usually smaller than the actual span, right? As in, it has to be smaller than the actual span because that's what a flexural span is, right? Okay, and then that's for a simply supported case. So for a cantilever case, we have to find that moment at the support because again, it's the max moment, right? Again, we have to find all of these at the same cross section. So if we're analyzing a cantilever the entire time, we find that IG, I cracked, and this short-term moment at the support, right? You have to stay consistent with where you're checking the cross-section, okay? And for a continuous case, it's actually really hard to calculate the bending moments for a continuous beam, right? So we actually have to use the simplifying method, right, which I'll show you below. This table, right, it uses this term called FD, which is a strength, what do you call it? It's like W star factored for strength, kind of, right? So instead, we have to adjust it slightly, and it's called FDEF. And this is what we use for serviceability, right? And it has this formula, right? And again, we only really have to calculate this when we're doing a continuous beam where it's really hard to find these values through normal 1300 analysis, right? And we have to calculate this creep shrinkage factor. It's based on how much compressive steel you have. So if you have 0 compressive steel, this number's 2, right? If you have the same amount of compressive steel as tensile steel, what happens to this number? Sorry? Oh, I know what you mean. Yeah, like this whole ratio is 1, right? Which means the overall number is 0.8. Very good. So it can't be less than 0.8. But I've got a question for you. Would you ever put more compressive steel than tensile steel?
Yes, if you want me. No.
Yeah, exactly. So if you do put more compressive steel than tensile steel, you're a fucking idiot anyway. So like, this number shouldn't be less than 8 anyway, right? But those are the two extremes, yeah? So 0.8 is if you have matching compressive steel as tensile steel. And 2 is if you don't have any compressive steel, right? Okay. Oh, and then you can look at this more later, but this is the simplified methods. I've just color coded it because the fucking code is so AIDS. Like you try to read this, it gives you headaches. So I literally had to draw it out. So there's different numbers for if you only have 2 spans and 3 or more, basically, right? And then the negative moments are in this top part. So these are the hogging moments that are described. And then the sagging moments are, yeah, they're in the middle, right? And this is based on end span, interior span. These are both definitions for end spans, right? Okay. Oh, also one question that people have sometimes is why isn't there a moment here? There is, but the code only defines it for the edge of the column.
Spectrum.
Yeah, outermost, but like it's fine because that's the cross section we're analyzing anyway, right? Yep. Okay, here's your big mama formula basically, right? This is the big mama formula that we've been working towards, right? Okay, So, firstly, before you do any of these calculations, you should check if your moment at that particular section, the cross section you're analyzing, is cracked or not. So what determines if it's cracked? It's on the screen here.
If M star section is greater than M star, M are cracked.
Very good. So again, what is M cracked?
The moment it starts cracking.
Yes, true. But it's like a threshold number. So I'm going to use the bucket analogy because I like to use, like, it's very simple. Like, M cracked is like the size of your bucket, right? It's the volume that your bucket can hold. And if the amount of bending moment at your section is more water than what fills your bucket, your section's cracked, right? And if it's not, then you actually don't have to use this big mama formula. In that case, the effective is the same as the uncracked moment of inertia. So it saves you a lot of time in your calcs. Okay. But in the case which it is cracked, which is probably what they're going to test in your tests, right? Otherwise, there's no point in doing half these calculations, right? Then, okay, we've calculated I cracked. That was in the first step. We've calculated IG, which is in the first step. We calculated M cracked. Okay, so with M star, right? This depends on the section, correct? So if we'd have a continuous beam at an end span, just let's say, how many sections are we doing?
Continuous beam.
Continuous beam, end span, how many
3.
sections? End span, not interior span.
1. 1.
2.
2. Oh, both ends.
Middle and continuous end. Right?
Inshallah.
So we're analyzing 2 sections. And so how many IEFs are we going to have?
2.
Very good. So what changes in this big mama formula is only M a star. Because M a star is going to change whether it's in the middle or, on one end, right? So, trying to think if there's anything else for that. Okay, basically there's also a maximum limit that this number can be, right? It's called IEF max, right? All right, so what is PW? Does anyone remember? Tensile Rio ratio.
Rio.
It's this one, right? Right? We calculated that earlier. If that number is less than 0.005, then this value, the maximum number it can be for IEF max is 0.6 Ig, right? But if the tensile Rio ratio is bigger than this, you can have it as just Ig, that's the max. Okay, basically the reason is because if you don't have enough tensile reinforcement, basically, right? That's what this case says at the top. If you don't have enough, like based on your section size, then your effective max section, and like if it's already cracked, it's going to be a bit weaker, I guess. If you don't have enough tensile steel, right? And then do you see how all these numbers plug in? So your average, right? So let's go back to that case where you have a continuous beam end span, right? So again, how many values do we have for IEF? Exactly. So we have 1 at the mid and we have 1 at the continuous end, right? So you literally just plug it in and it has equal weighting to these. But if you're doing an interior span, it has 1/4 weighting for both the ends, right? So they have different weightings, right? So like, again, we're looking at this, right? Basically, we're saying that the weighting for the average is 50% here and 50% here, right? For the continuous interior span, this one, 50% weighting here, 25% weighting here, and 25% weighting here. Makes sense? For this one, 100% weighting. For this one, 100% weighting. That's how the weighting system works for your average, right? Okay. I don't know if I'm gonna have time to deal with this. Let's go back to deflections. So what was AIDS was calculating that Big Mama formula. But now we have something to express the moment of inertia for the entire beam span that we care about, right? So now we just simply use, what's it called? Solid mechanics, right? It simplifies the really complicated behavior of concrete into something as if it was a very simple material like steel or whatever, right? And then beta is like based on your like loading case, right? So there's a bunch, I've highlighted them in, so this is like loading and support case. I've highlighted them in blue there. You can use the flexural span if it's given, right? You have to be really careful of your units here. If this is in millimeters, then this will be in millimeters. But if you chuck in meters, if you chuck in meters and then this is in MPa and this is in cubed, you're fucked, right? You get a really incorrect number. So make sure your flexural span, which might be something like this, if it was 7.4 meters, make sure you convert it to millimeters. Otherwise, you get almost like a really cooked value, right? And then for continuous case, you have to use a slightly different method. You can't use this beta method. You have to, it's like this is your serviceability weighting at the middle, short-term weighting in the middle, and that's on the left and then the right, and etc. Okay, I'm nearly done. So sustained deflection. So I've kind of avoided talking about sustained deflection, but sustained deflection is a mathematical step in the middle, right? All it is instead of whenever we use the short-term factor, right? So remember your short-term factor was something like 0.7. The long-term factor is something like 0.4, right? So this sustained deflection will be a lower number than your short-term deflection. But instead of doing all our calcs all over again, we literally just divide out the short-term and then multiply it by the long-term. And boom, we'll all of a sudden have our sustained deflection value. You can just read this. This is a really minor point. But then I was talking about the creep shrinkage factor again. It comes up again at the very end here. So this is to do with your compressive reinforcement amount. And then your long-term deflection is that value. That value multiplied by that sustained deflection. And then when you add those both up, the long-term deflection and the short-term deflection, you get the total deflection. And that's how you solve the question. Oh, well, you have to compare it to the limit, but the limit is literally just from the table. Yep. That makes sense? Okay, I've got to pack up.